Chance Encounters and Innovation, titled Varying Serendipity Between Inventors. I think it's a timely topic, you'll find, given the current situation with the COVID pandemic, though I did not know what was about to happen when I started this project last year. I'll begin with an outline. I'll start with my research question and motivation. Now I'll move on to my theoretical approach, presenting my argument and hypotheses. Then I'll present my empirical approach. Discuss how I construct my novel independent variable and how I validate it. And I'll test my hypotheses, present the results, and conclude with a discussion on how my results may generalize to some current issues around COVID-19. I'll start with my research question right away, though I'll be returning to it. And a definition of a key term I need to be very clear about right up front. My research question is simply, what is the effect of chance encounters on innovation? I define chance encounters as unplanned social interactions between people who happen to be at the same place at the same time. Like scheduled meetings, phone calls with friends are not chance encounters because they're planned. The chance part is that the encounter is with who is nearby for whatever reason. So we know that knowledge workers are the fundamental unit of knowledge in an organization, and their search for knowledge to put into new or better combinations is a core process that results in innovation. So during this inventive search, as Fleming 2001 calls it, inventors usually rely on salient, proximal, and available knowledge because of their own bounded rationality and the tendency towards local search. But proximity doesn't just constrain where knowledge is looked for during inventive search. We can also look at proximity to other people as a force enabling new pathways for someone to learn and get new knowledge. Research shows that close physical proximity between people can increase the likelihood of chance encounters in a way that increases awareness of others and awareness of their knowledge, and it can form social relationships, all of which can lead to a collaboration between the two. Even short social interactions can increase awareness enough to play a large role in collaboration, as Baudreau et al. Here show experimentally. And unplanned short social interactions can be enabled by proximity. This is what I'm calling a chance encounter again. Innovative output, aside from just like knowledge transfer, like a spillover outside a firm, requires a certain amount of collaboration and aligned goals, which occurs when there's no organizational constraints. So productive proximity likely normally occurs within an organization. However, proximity does not only affect chance encounters. It also increases the richness of communication. Like much more is ultimately communicated in a face-to-face conversation than otherwise. Proximity also increases the ability to schedule planned interactions, even for work or for socializing. It also generally increases trust and feeling of affiliation with proximate people, in part through these above activities and potentially on its own as well. So chance encounters are understudied as a phenomena as something separate from proximity because they're hard to study. But it's easy to imagine that these other effects of proximity have their own effects on innovation. Proximity and chance encounters are conceptually different things then. So to better understand the effect that proximity has on innovation, we should separate these. We also have several modern day motivations to want to understand chance encounters right now. So first off, there's plenty of anecdotal evidence that chance encounters affect innovation. The Nobel Prize for Medicine in 2003 was awarded to Paul Lauterbur, who said a conversation over hamburgers led directly to the development of the MRI. And another more recent Nobel laureate, I actually really like looking at the Nobel laureate interviews because they always ask how their research and development started. That you don't do that, like patents don't have that kind of information. And a lot of their stories seem to start this way. This Nobel Prize winner, Jennifer Doudna, said just a couple weeks ago now, thinking back on it, it really began when I moved my lab from Yale to Berkeley. I had a conversation with Gillian Banfield, who told me about evidence for a bacterial immune system called CRISPR. So think about that. She moved her lab, ended up talking with Gillian, who she's newly proximate with, another researcher, and that set her off in this whole new direction that really changed science now. Gillian, her collaborator that she's mentioned that did not win the prize, was also interviewed. She says, every now and then Jennifer and I met, usually at the Free Speech Cafe, and talked about collaborating. She adds at another point in the interview, it was serendipitous how they met. There's also a relatively current trend now of designing workspaces to encourage this type of social interaction between employees. The idea being they'll work with each other more, ideas will spread more freely. Apple's Apple Park in Cupertino really exemplifies this. It was Steve Jobs' last project with Apple helping design this building. Now, Steve Jobs was known at Pixar for seating employees with the longest possible walk to the bathroom, so that presumably on the way back, they have more opportunities to interact with other employees. Now, if the thought of being in a facility like this Cupertino facility with 12,000 other people in a building designed specifically to make you bump into other people kind of triggers a COVID-related gut reaction that you'd really rather avoid this place right now, I'm going to want you to hang on to that feeling for when I talk about my research design. So of course, there's a bigger trend now. The COVID-19 pandemic changed everyone's lives in a way that decreases chance encounters. We're actively avoiding people, even if we're near them. Many people are working from home, and chance encounters, remember this was 3 years ago, it was a big deal then, now it's every single day. Chance encounters are only with close family at whatever age. And I'll discuss what's happening, what I think is happening during COVID, and what might be able to happen afterwards after my results, because I believe my results generalize to this type of situation, at least in one important way. Now, policymakers and business leaders are starting to rethink working practices, and I think having a fuller picture of the proximity to others that a work location outside the home offers someone, a picture that explicitly includes the effect of chance encounters, will be important to deciding how we all might go back to the office and when that's an option, or when that is an option for us to do that responsibly. Now, my research question again is, what's the effect of chance encounters on innovation? My argument comes from the fact that chance encounters are unplanned. So when knowledge is transferred because of chance encounters, they can break the tendency towards technologically local search, resulting in more novel recombinations. So I'm presenting an updated theory of inventive search with knowledge substitutions to model inventive search to theoretically describe the counterfactual to innovation affected by chance encounters. So in other words, if there were no chance encounters, what would have happened? So what happens if potential chance encounters decrease? So inventors generally have a goal of developing technology, either directed by their employer or themselves. They still go to work. Chance encounters are not the way that inventors are expecting to develop technology. There are other ways available. Engineers don't just show up at work with nothing to do, hoping to bump into someone. They have something to do. The other ways are more directed, and therefore they're probably more subject to the tendency towards local search. Inventors are likely to seek sources of knowledge where they have experience. And reusing the same sources of knowledge over and over leads to less novel recombinations. So my first hypothesis is, when there is less opportunity for chance encounters, the novelty of innovation should decrease. But where do they look? Knowledge is often sought in other people. The choice of person to ask is determined in part by awareness of what the other person knows and perceived lower cost to access that person's knowledge. So prior contacts represent an easy first stop, because inventors have a high awareness of what their prior collaborators know and trust they can work with them because their shared working experiences already working with them. Seeking knowledge in prior contacts is likely an early direction of search. So generally, inventors will look more to prior contacts as an early choice for knowledge. If chance encounters provide an answer before that, then the inventor may not need to actively search and will not look to prior contacts. So my hypothesis 2A is, when there is less opportunity for chance encounters, inventors will work with prior contacts more often. And because awareness and trust increase with the more experience with another person, this effect should be more intense for the deeper prior connections. So hypothesis 2B is the effect of 2A should be greater for repeated contacts. Now, in these arguments, I'm effectively saying that inventive search is a type of individual problematic search. Probabilistic search stops at the first satisficing solution. For this case, a solution to inventive search is an adequate recombination of components. Probabilistic search also adapts until a solution is found. So in this model, inventors are not looking for all possible recombinations of components and knowledge, which is really an unreasonable cognitive task. More information does not always lead to better decisions. Instead, if a problem is not solved by one method, so by bumping into somebody who happens to have relevant knowledge, it may be solved by the next, which is asking your colleague. You usually ask about this. So because my model assumes that net productivity might not change because of ready substitutions for chance encounters, I explore that in the empirical section. So to wrap up my front end here and illustrate my research question and introduce the empirical design, I have a couple scenarios I'm effectively asking what is the difference between. First, we have, make sure this works, have an office with plenty of opportunity for chance encounters. There we go. People are buzzing, people moving around, talking with each other. Second scenario, now people are scared of getting sick. You hear about flu on the news, you hear a cough in the break room when you come in the front door. Might look a little more like this. People are keeping their nose down. It's the same office, with the same people, the same jobs, the same tasks they had before, the same expectation to be able to work with each other into the future, the same trust, all these other things that come with proximity, just fewer chance encounters. Now, my empirical approach, how do I apply this second condition? I've already given it away more or less in a broad stroke, so I'll describe how I do it. I'll start with the empirical challenges. First, measuring chance encounters directly is really difficult. And changing proximity has been used as a proxy for changing potential chance encounters in research. But proximity also changes other related things, like richness of communication, convenience of meeting, right? These other things can also increase the quality of output. So they're confounding any effect of chance encounters if we use only proximity as a proxy. So the best existing research designs in this area show that proximity matters to innovative outcomes. And that's likely because of chance encounters with nearby people. And they do so by altering who chance encounters might be with. There we go. They do not vary chance encounters. Instead, the research designs assume that chance encounters generally happen, and they do, otherwise they wouldn't get results. So I owe a lot to this research because they show that chance encounters really matter, but we do not know yet if chance encounters themselves affect innovation, the nature of innovation. So back to empirical challenges again. I need to untangle potential chance encounters from proximity. To address these challenges, I turn to findings from the subfields of public health called social epidemiology and economic epidemiology. My approach goes, the fear of catching a disease can lead to a social avoidance behavior by a significant portion of the population if certain conditions are met. And they are that people are aware of the disease, people fear catching the disease, and people believe that social avoidance can increase their safety. And the flu meets these criteria, and studies from historical and modern data quantify social distancing from the flu. And yes, social distancing is the term. Don't think about how it's used now. It means a lot of things now. I don't mean 6 feet away. I don't mean directive from the government. I mean a voluntary behavioral response. And that's why I've used the other term. I shouldn't have even said it, social avoidance. This is because it meets the criteria because the news commonly reports the flu, increasing awareness. The flu is feared. Surveys show that it is feared as much as cancer and heart disease. And people avoid each other others when they know the flu is present. Multiple studies show this behavior using all sorts of measures. This is really an established phenomenon. And importantly, one easy answer for the why not use coronavirus for this type of research question is that life goes on. People go to work. Projects are uninterrupted. We have to think back of how the flu treated us before. It was not a huge deal, but it was for some people. So I'll go into that a little bit. Also, as I think I said, I started this project before the coronavirus pandemic, so this is not a project about disease. And then again, and also COVID is a very messy shock. So to get a little deeper into the social avoidance behavior and how it decreases chance encounters. People afraid of the flu will avoid others. It'll look a little more like this. The people who are nearby, the proximate people feel less proximate in terms of chance encounters. People engaging in social avoidance will decrease their own rate of chance encounters, but doing so also decreases their availability of chance encounters with others. So the opportunity for chance encounters for many people decreases because some people engage in social avoidance. So to test my hypothesis, I construct an independent variable as proxy for lower levels of chance encounters that may have affected an innovation. That is the duration of local flu during inventive search preceding an innovation. In other words, more flu during inventive search proxies for a lower level of potential chance encounters affecting an innovation. The next section describes the construction and validation of this measure. So for the period of inventive search, I choose a 1-year window prior to a patent application date. This range has the benefit of removing seasonality, and it reflects the continuous nature of projects that have patents as output. As most valuable inventions of products or processes actually result in multiple patents over the time of their overall development. And the patent is not the end. The beginning of the project is not the beginning of the patented element of that project. I have another project where I focus on estimating what inventor was involved on the work of a patent. It's kind of a spin-off of this paper. So I can actually talk about this choice of 1 year at length if you want, but for now I'll leave it here and also say that I also estimate with other windows, and the results are consistent with expectations for that. So let me illustrate an example of the independent variable. The pink area is the independent variable over time for a state, Indiana. The y-axis and pink area is weeks of prior flu within the last 12 months. These are the application dates for 3 patents, patents A, B, and C. This window, this blue bar, is the window of the search time before each. These vertical lines represent weeks of widespread Indiana flu. The term widespread is the indicator from the CDC, the Center for Disease Control, that the flu is both spread out all over the state and is at a high level. Widespread is what's reported on in the news. It's the highest level that there's reported. And you can see that patent A was, I think you can see it, was likely affected by a lot of flu. Patent B was less, and patent C, no flu at all. Now, I didn't pick Indiana because it was an outlier or anything. This is a normal state with a normal amount of flu. Here's a graph of the distribution of this variable. I actually picked Indiana because I personally was an inventor in Indiana during this time, and I'm in the data here. You can see on this graph that the distribution of prior flu may have more variance than you were expecting. A good 14% of the sample has no exposure to the flu. The average is 6.2 weeks of flu, and the max is a whopping 37 weeks of flu. You can see that was pretty uncommon.
Sorry, just one clarification. Are you considering in your study just the classic flu or other type? I don't know, since we are now talking about COVID, there are also other type of flu that could hit some countries more than others. So just, yeah, if you can explain this.
Yeah, it's the regular seasonal flu. In 2008, 2009, the swine flu kind of replaced the regular seasonal flu. So I do have that in here too. It has kind of qualitatively different results, but it doesn't change anything if I take it or to put it in or take it out. But yeah, I'm just using flu. Yeah. So there's a significant amount of variation of flu within states as well, which is important because that's where my variation is coming from. And in the timing, which I'll show you briefly here. So there's no pattern I can find, I'll tell you first, but I do use Inventor and state and year month fixed effects if you're thinking about my estimation model right now. So let me show you the first 3 seasons. There it's going. First 3 seasons of flu in the data. I won't show too much of this because I know people glaze over, but you can see it starts in a different part of the country, lingers some places and not others. If I showed you all of it, you'd start getting very frustrated there doesn't seem to be a pattern you can find. And well, yes, these are the struggles of epidemiology as a field, but it's fairly unrelated to someone's individual search processes. So to validate my independent variable, I run several tests that show that flu search represents less potential chance encounters during search. I have a lot of validation tests actually, that it's becoming another chapter in my dissertation and potentially a separate paper. Validating the measure is not the point of this presentation, but it's important because it's a new measure, so I'll give you the highlights. The logic of validation tests begin with the fact that chance encounters are only with geographically local people. When the opportunity for chance encounters decreases because of more flu, an innovation should have fewer local collaborators, all else equal. So to test this, I use a monthly panel of about 271,000 inventors of multiple patents within the US between 2004 and 2015. This is where the CDC data is available. So I test several models. In the main validation test, I use fixed effect Poisson regressions. I regress local collaboration count, which is the dependent variable on weeks of prior flu, the independent variable I use that I just described. I use inventor fixed effects to see the change in an individual. I use state indicators in case people change states. Otherwise, that would be absorbed in an individual fixed effect. I use year-month indicators for overall trends and also controls for monthly personal collaborations. I find that there are about 1% fewer local collaborations with average flu versus no flu, which I feel supports the measure. I don't stop there. I test several corollaries and robustness tests to predict and test expected relationships of this effect in different conditions. One of them is I find the effect is stronger when inventors can choose their own collaborator, are more likely to a priori able to choose their own collaborator rather than it being assigned, rather than the collaborators being assigned to them. The effect is also stronger when an inventor has more non-local options of a collaborator. And I find the effect is sensitive to timing when it should be. There are a few industries that move a little faster and they are more sensitive to a smaller window. And I can talk about this too much actually. So that's why I'm splitting this off into another paper, but there's quite a bit. Not to dismiss feedback on it though, I need that too. Now to test my hypothesis. Now, to remind you, it was, when there's less opportunity for chance encounters, the novelty of innovation should decrease. Empirically, novelty should decrease when the flu increases. So the independent variable is what I've been describing, the weeks of flu prior 12 months. The dependent variable is a common measure for the novelty of patents from the OECD called the originality index. It's a continuous measure of the novelty of combinations of cited technology classes. So I run 2 separate models. Because geography is based on the inventor, but novelty is on the patent, I use inventor patent observations with that inventor's geography determining the independent variable in one model, and then aggregate patent observations with averaged flu between inventors in another model. I use the same sample of multiple inventors and their patents from the validation test. I use a simple OLS to regress originality index on the flu variable with the year-month indicators for overall trends and state indicators for the first model. Now my results support hypothesis 1. I show lower novelty of innovation when there's more flu, and it's in both models. My second hypothesis was when there's less opportunity for chance encounters, inventors will work with prior contacts more often.
It's sorry if I interrupt you. There is a clarifying question. How can you verify if the inventor could choose his collaborators or not?
It's a good question. I turn to other literature for that. There's two different tests I run for that. There's one that says that smaller companies and like startup companies will have to use, people have to use their own networks a lot more. So I use small and new companies as a proxy for if they can pick their own. Also, I run another test where academics might be able to pick their own collaborators more. So I use that as well as the conditions.
Thanks.
So the second hypothesis, right, was when there's less opportunity for chance encounters, inventors will work with prior contacts more often. So empirically, that is more flu, more likely a co-inventor is a repeat. The second part to that is that the effect should be greater, more often, for more often repeated prior contacts. Again, the independent variable is weeks of prior flu. The first dependent variable is a count of new contacts that month, which is reverse coded from the hypothesis. So we're expecting a negative value here. And the second dependent variable for H2B is the count of prior collaborations with all co-inventors that month. So an aggregate count. There's a monthly panel of the same multiple inventors as before with fixed effect Poisson regression using state and year month indicators again, this time using a count of unique co-inventors that month as control. You see that the results support my hypotheses. Model 5 tests hypothesis 2A, and model 6 there tests hypothesis 2B. Model 5 shows that flu is negatively associated with new contacts, so it's more likely these are repeats. There are only two options, new or old. Model 6 shows that the weeks of prior flu is positively associated with how many times an inventor has worked with their co-inventors this month. So it's not just new versus repeat, but the more repeated they are, the more they are collaborated with when there is more flu. So one might also ask, how does this affect overall productivity? Because knowledge sources substitute in my model is assuming that net productivity may not change when potential chance encounters decrease. This is an empirical question, at least how I see it. There are three potential scenarios. The first is, if chance encounters only add to available knowledge, fewer chance encounters should lead to lower output levels. And in this case, my model is probably wrong. If chance encounters are substituted for efficiently, there may be no effect on output, and this is situation B here. Or if chance encounters are less efficient sources of knowledge, and they might be inefficient if they're more exploratory, because exploration is inefficient, and we know they're more exploratory because of the first hypothesis, then productivity may actually increase. From a firm's perspective, this is an important consideration if they're thinking about trying to encourage chance encounters, especially if the goals of the firm are more exploit than explore. They might be hurting themselves by inadvertently encouraging exploration instead of more efficient exploitation. So this is how I test this. If the flu affects productivity, we should see the timing of applications to be affected by the flu. So our application times preceded by more flu, more or less productive, or is there no change? So for all prior models, they were all conditioned on output. Patent applications exist that month. That's how I know about collaborators and their novelty, et cetera. But to test productivity, I need a different approach. So I create a panel of the same inventors and compare when they were productive versus when they could have been productive, which I define a few ways in a few different tests, but in the one model I'll present as they could have been productive between applications that I witness and a year or more or less from the first and last. Each month is coded as 0 or 1, so productive or not, or productive. patent application or no patent application that month, which represents the search window, the prior search window of a year. I find that productivity is weakly positively related to the flu variable. That is, more flu, more productivity. I don't want to overstate this finding, however. It was just from a suggestion to see the bigger picture. I'm happy that productivity doesn't go down because my theory of substitutions would be more questionable if that happened. Plus, the association is weak in my best model testing this with a p-value of 0.06. So I don't want to read too much into it, but I figure it's worth mentioning because this is a consideration in probably some of your heads right now. Now, I want to move on to the discussion of modern day implications of this. Let's go back to this slide, remind you, as if we need a reminder, right? COVID-19 pandemics changed everyone's lives. Chance encounters have decreased. My findings should generalize this setting to a degree. People working from home, chance encounters are with close family, and working from home is a trend that seems to be sticking. Many leading innovative technology companies switching to working from home long-term, even Apple on the bottom there, saying things will not return to the way things were. Invest billions of dollars in this big building. But this is what they're saying now. So the question I let hang at the beginning is a real one. Will we go back to the office? In some areas, policies are being created to make working from home more of a norm or a protected right well into the future. So we might not go back to the office, or if we don't go back to the office, what are we losing? We have some sophisticated ways of replacing some aspects of proximity, like richness of communication. There's virtual face-to-face meetings like Zoom, virtual whiteboards, other new technologies we're all pretty used to by now. Also, it's pretty easy to meet anyone now. You don't have to meet in person to meet. Those barriers are lower. And you can even socialize online. By the way, everybody pictured is a job market candidate this year, and I recommend them. I see one of you shaking your head at me. You're welcome. But these meetings are all planned. Even the meetings to socialize, it's planned. And when you plan a meeting, it's with the same people you already know. The chance part is missing. So now I'm not talking about working from home in this presentation explicitly, but it's undeniable that working from home decreases chance encounters. And it's worth knowing how that change will affect innovation, especially for innovating firms. Long-lasting changes towards working from home, the way things that are sounding like they're going, may result in lower novelty of innovation into the future, but potentially more efficient, I don't know. Knowing that's a side effect of working from home will help organizations plan given their own goals. So now my conclusions. Chance encounters divert inventive search away from familiar sources, changing the nature, not necessarily the quantity of innovation. Innovations started by chance encounters are likelier to be more novel and more exploratory, whether or not that's what a firm might want. Staying home will likely result in less novel innovation, which might be what a firm does want, depends on the firm. Chance encounters are less replaceable by technology than the other aspects of physical proximity, I would argue. And when firms make the decision to go back to the office or not, they should consider the effect of chance encounters that I highlight as a key feature of in-person proximity. So thank you for listening to my presentation. I look forward to your comments.